Okay, class, let's solve some problems. I'm going to put this on a new page and start from scratch. There we go. Okay, so I think the question asked us to find the node voltages, calculate the node voltages. Well, let's look at this guy. I don't see any node voltages. I see some names of node voltages. I can see over here, let's get my little laser pointer. We have V1 and V2. Those are the two node voltages. There's also a third node here, which is the ground node, but the ground node is assumed to have 0 voltage, so everything is referred to it. So we've been working on nodal analysis, which means that we're going to take KCL expressions applied at each node and use those to balance the currents into and out of the nodes, and then convert those current equations, when possible, into voltage-based equations by using Ohm's law applied to the resistors that are connected to each node. So let's see how this works. It's pretty straightforward. I'm going to start with this node here, V1. I'm going to write KCL for that node. So I like to do something like this, KCL at node 1. And I'm looking at that node, and I see that there's 3 branches connected to that node. So starting with this branch right here, I see that that branch is carrying current I1. All right, I1. And I'm going to take the current into the node as positive and out as negative. And I'm going to do that for all of my nodes, and you'll see what will happen. I think the problem solves it a slightly different way. Let's see if we get the same answers. So I get I1 in, and then I get I2 out, so it's going to be negative. And I get I3 out, so it's negative. And those 3 things have to equal 0, because the current going in will equal the current going out. Now, while I'm on the node, I'm just going to go ahead and convert these currents into voltage representations when possible. So the first one, the I1, if I look at it, it's given as 5 amps. You see, it's the same current. So I1 is 5 amps. So let's just put that in there. It's in the same direction. The 5 amp source is in the same direction as I1, so I don't mess around with the signs of it. Now for I2, check this out. That's the current through this resistor, right? Well, I can find the current through the resistor if I take this voltage minus this voltage. And why is it plus minus like that? Because I put the plus sign on the end of the resistor that I2 is going into, right? So the voltage at this end is V1. We don't know what it is yet, but we have a name for it. So I'll use the name for it, V1. And the voltage at this end is V2. So I have V1 minus V2. That's the voltage across the 4 ohm resistor divided by 4 ohms. That should be the current I2. So you see, I1 is 5. I2 is V1 minus V2 over 4. And the third one, this guy, we're looking for this current. Again, I'm going to mark this as the plus side because the current goes in on that side. This is the minus side. The current's going out on that side. And I know the resistance, it's 2 ohms. So I can go ahead and I can go for I3 will be V1 minus 0, because the reference node is 0 volts, divided by 2. And all of that is equal to 0. So that is KCL at node 1, this expression. Now we're going to do KCL at node 2. Okay, same idea. I'll put a little circle around my node, and then I look where the branches intersect my little circle. And I'm going to call into the node as positive and out of the node as negative. So it happens to be the same thing I chose for the first one. So if I look at what's going in, I see I4. I see plus I2. I see minus I1. Now, where did that come from? Well, it's the same I1, right? This current is traveling on that branch. So this is also I1 over here. And then what am I forgetting? I5. So I5 is this one. So again, I'll take that as the plus node, that is the minus node. Current for resistors always goes in a plus node by passive sign convention, unless it's labeled wrong. But we're going to label these things correctly. So minus I5 equals 0. And now I can start knocking a few of those off. I see that I4 is 10 amps. I2. Now, I used the same direction of I2 as before, right? It was in this direction. So I can use the same equation as before. I'm just going to copy it down from up above. It was V1 minus V2 over 4. Then you might get confused. Why was this a minus and down here it's a plus? Well, in this case, it was exiting the node that we were talking about. In this case, it's entering the node that we're talking about. Hopefully you see that. Then we have I1. Where's I1? Oh, I1 is our buddy, the 5 amps. That's leaving the node, so that's minus 5. You'll notice for the KCL at node 1 it was plus 5. Now it's exiting the node. And then we have I5 will be minus, right, because it's exiting the node, V2 minus 0 over 6. And all of that is 0. So that is our expression at the other node. Now, because I'm very lazy, I'm not going to solve these. I'm just going to comment that we have two unknowns present in both equations. So with 2 unknowns and 2 equations, we should be able to solve for V1 and V2. You guys try it. And when you do that, where's the solution here? When you do that, you should get 20 volts and 13.33 volts. 20 volts and 13.33 volts, like this. I'll mark them in here for you. I'm going to get 20 volts here and 13.33 volts here. Now that's interesting because that voltage, this one, is higher than the 13.33. So the current through the 4 ohm will actually be in this direction. So if you solved for I2, you should get a negative number. Was that done here anywhere? Well, I guess not. You guys can do that. Solve for I2 to prove to yourself that when you solve for that, you're going to get a number that's negative, telling you that I2 was chosen in the wrong direction, right? I mean, it should be, when you solve for I2, it's going to be, oops, I need my real pen, 13.33 minus 20 divided by 4, whatever that works out to. That's going to be a negative number, so that many milliamps will be flowing in this direction.